The James Webb Space Telescope is now 1 million miles from Earth and performing science operations. The Nancy Grace Roman Space Telescope is scheduled to launch by 2027. These two observatories are NASA's latest flagship missions in the tradition of Hubble, Chandra, and Spitzer. But why do we need both? And why do they look so different? The answer to both questions is that they are built to do different things. Webb has the exquisite sensitivity and wavelength range to capture detailed images deeper into the universe than ever before. Roman has an incredibly wide field of view to rapidly survey huge areas of sky while still rivaling Hubble and Webb's resolving power. Webb will tell us about the early universe, and Roman will help us understand how it evolved from there. One of the keys to Webb's sensitivity is its huge mirror. At more than 21 feet wide, it's the largest mirror that has ever flown in space. By using such a large mirror to collect more light from faint objects and observing in infrared wavelengths, Webb will peer deep into the distant early universe. The universe's expansion stretches light traveling through space, a phenomenon called redshift, because the light waves we receive from receding objects are stretched to longer, redder wavelengths. Webb is designed to see this redshifted light so that it can study the first, most distant galaxies. The Roman Space Telescope, on the other hand, isn't trying to see quite as deep into the universe's history. Roman does have filters to see infrared light, but not as far into the range as Webb, because its targets aren't as redshifted, and Roman's mirror can be smaller because it isn't trying to detect such faint objects. That wavelength difference affects another very visible feature of the two spacecraft. Webb observes light near the same wavelengths that the spacecraft itself would emit if it were not cold. As a result, Webb has a very robust system, including the multi-layer sun shields, to keep it extremely cool. Roman, on the other hand, needs far less cooling because it will observe in wavelengths unaffected by a warmer spacecraft, so the shade provided by its solar panels alone does most of the work. While Webb will peer with intense focus at very specific objects and regions, Roman is a survey telescope designed to capture vast swaths of sky. But it will do so with revolutionary precision, sensitivity, and depth. The key to doing this is the heart of Roman's wide field instrument, a massive camera with 18 next-generation detectors. Each one captures a 4,000 by 4,000 pixel image, and together they will take pictures covering 100 times more sky than either Hubble or Webb. This wide view will allow Roman to study enough large-scale structure of the universe in high precision for scientists to begin understanding its true nature, including dark energy and dark matter, and viewing early galaxies as a population rather than a few individuals who may or may not be average. Both telescopes will also help us learn more about planets outside our solar system, called exoplanets, but in very different ways, with Roman finding more that were previously undetectable, and Webb gathering new details on those already discovered. These two telescopes, with their different complementary goals and strengths, will help us understand much more about the early days of the universe, how it has evolved since then, and what other worlds might be out there. The Nancy Grace Roman and James Webb Space Telescopes have very different approaches to studying the universe. Roman has an extremely wide view to capture as much of the cosmos as possible. Webb will peer deeper than any telescope before it to see more detail and farther into the past. These contrasts enable different science and help us answer separate questions about the universe. Webb will see galaxies that are extremely far away, whose light was emitted when the universe was very young. It will reveal an early universe that scientists have only explored through calculations, We have very little information about the cosmos' infancy, and Webb will help us fill in many of the gaps in our understanding by making direct observations of galaxies as far into the past as physically possible. Roman, on the other hand, will use the power of its wide sky coverage to survey massive regions of space, documenting significant portions of the universe through its adolescent and early adult years. Not only does Roman have a field of view 100 times larger than Webb's, but its compact and rigid design makes it more nimble, able to quickly repoint that wide view to survey large regions through a process called tiling. Roman will be able to survey thousands of square degrees of sky during its primary mission, enabling studies that were never possible before. Only by studying hundreds of millions of galaxies can scientists begin to determine the behavior of the universe as a whole, its large-scale structure, and how it has changed over time. Dark matter and dark energy are both large presences in the universe that are only detectable through their effects on normal matter. The brightnesses of faraway supernovae work to measure the distances of galaxies and how dark energy is pushing them apart. The precise shapes of galaxies serve as a way to study the dark matter around them, but these features must be measured very accurately to be usable. Roman's hardware is particularly precise and well understood, so the data it collects is especially good for the statistical analysis required, giving scientists a holistic view of how dark matter and dark energy exist and affect the visible universe. Previous great observatories, Hubble, Chandra, and Spitzer, greatly expanded our understanding of the universe. Some of it was in ways that scientists and engineers had anticipated and designed the telescopes for. But many other discoveries were unanticipated, as the great observatories revealed new aspects of the universe and scientists discovered creative ways to use these powerful tools. The same will be true of both Roman and Webb. We can anticipate some of what they will show us, but many of the most exciting discoveries are the ones we can't predict. Out there, about 1 million miles from Earth, Webb is already drinking in faint infrared light from the first galaxies, turning whispers from the early universe into detail we can actually read. And soon, Roman will join it, not to zoom in, but to widen the story, mapping huge regions of sky, catching cosmic changes in motion, and revealing patterns that only appear when you step back. Together, they're not competing, they're collaborating. One telescope dives deep, the other sees wide. And in that overlap, the universe starts to make sense. Thanks for traveling this stretch of the cosmos with us on Wormhole to Cosmos. If you enjoyed this series, give it a thumbs up, drop a comment, and subscribe for more journeys. Remember, the universe is vast, mysterious, and full of wonders waiting to be explored. Stay curious, keep looking up, and until next time, keep your eyes on the stars.